Okay, so today I wanted to talk about elementary properties.
There is a problem with the sounds.
You can't hear me?
No, but it's okay.
Досить далеко.
Okay, I will try to speak louder. Can you hear me now?
But now there is a noise.
Okay. And now?
Speak something.
1, 2, 3.
Okay.
Супер.
Okay, so today I wanted to talk about elementary properties of category of sheaves. On the site. My talk will be rather brief. I think we will end like 40 minutes. So I'm sorry for that. Maybe it's good. I don't know. Okay, so let's fix the setup. Let's see, be a small category with Grassendick topology J. Let us write down the junction which we established last time. Yeah, the sheavification functor was defined last time. And recall that arbitrary limits exist in category of sheaves. So, and they're computed pointwise. So we have, recall, we have a formula. In category of pre-sheaves. Last time we have shown that the category of sheaves is closed under small limits, and they're preserved by the inclusion functor, as the inclusion functor is right adjoint. Okay, in particular, we see that the limit of an empty diagram, which is equal to the terminal object, is in fact a sheaf. So we have a home functor, which is co-represented by this object. So and it is denoted like this, so it is a functor of global sections. Okay, this functor has a left adjoint denoted by delta. And it maps from sets to pre-sheaves like this. So obviously, the value of this joint functor on set S is a constant pre-sheaf. As we established earlier, constant pre-sheaf is not necessarily sheaf. However, if we combine it with, compose it with the sheafification functor, we will get the left adjoint for the category of sheaves. Let me write this down. So, so from the theorem on sheafification, we derive that there is a left adjoint to gamma from sheaves to sets, which is given by A composed with delta. And we will denote it simply by delta. Sorry for this slightly confusing notation, but yeah, so we get left adjoint. Okay, so now let's talk about mono and the epimorphisms of sheaves. So a morphism in sheaves. The morphism between underlying pre-sheaves since I is adjoint to A and phi is a monomorphism of sheaves, if and only if it is a monomorphism of pre-sheaves. In other words, I preserves and reflects monomorphisms. However, for monomorphisms of free sheaves, we have a very concrete description. So just a pointwise injection phi from F to G. So monomorphism of sheaves if and only if phi C is a monomorphism for every object in our category. The same holds for epimorphisms of pre-sheaves, but not for sheaves. Same holds for morphisms. Pre-sheaves, sorry. Pre-sheaves, but not of sheaves.
Grish, sorry, you mean pointwise epimorphisms through surjection, да? Yes?
Yeah.
Okay.
But it's not true for sheaves. Yeah. Okay, so another corollary of the theorem on sheavification is existence of small colimits in sheaves of on a side. Let me give a recipe for computing such colimits. So the recipe is quite simple. We just take a colimit inside of three sheaves and then we sheavify the result. So in sheaves on a side, we have the following formula. For colimit of sheaves. It's just isomorphic to sheavification functor applied to colimit of pre-sheaves. Okay, so since the colimit of pre-sheaves is computed pointwise, we see that we have the following formula. Sorry. Okay. So we have the following formula for the limit of sheaves. I can't explicitly write down this formula for sheaves because it involves sheafification, and it does not compute straightforward on objects. So we have just this formula. Okay. Our next goal is to construct exponential objects in sheaves. Assume that we already constructed such an exponential object. Then for we already have an exponential object. Then it is constructed just like in pre-sheaves. Namely, given two sheaves J and F, I of J to the power of F is equal to I of J to the power of I of F, where I is the inclusion factor of sheaves into pre-sheaves. The Ioannidis lemma now implies the following sequence of bijective correspondences. So a morphism given an arbitrary pre-sheaf P, we have a transformation from P to I of G of F. Now by jointness, we have this. Now by definition of the exponential object, we have the bijective correspondence of this form with maps of this form. Now, once again, because of the jointness we have and the fact that A preserves small limits, we have the following. Now we once again apply jointness. So all this levels of this diagram are bijectively correspond to each other. Because of adjointness, we have the following. And finally, since we have an exponential in pre-sheaves, we see that there is indeed a bijective correspondence between maps from P to IGF and maps from P to IG IF. Okay, so A is a left joint to I, and the composition AI is isomorphic to AD. A preserves finite limits. A of P times F is isomorphic to A of P AIF, which is in turn isomorphic to AEIF. So I just wrote down one of the steps here in this diagram. Okay. So now I formulate the following proposition, which is quite important for exponentials in sheaves. So proposition let P and F be two pre-sheaves. If F is a sheaf on the set Cj, then the exponential in pre-sheaves is also a sheaf. The proof of this proposition is quite complicated and very technical, so I will skip it in favor of giving two examples. But first, to give the first example, I will have to recall Grothendieck topology on complete Haitian algebras. Okay, so first of all, I will recall what is a complete Haitian algebra. Shortened to HA is a distributive lattice with the implication operator. Of the following form. So we have the condition that A is less or equal than B to C if and only if A and B is less or equal than C. Complete Haitian algebra, or CHA, is a Haitian algebra complete as a lattice. A supremums and infimums of arbitrary families exist. Okay, so let me give a useful property of complete Haitian algebras. If A is a complete Haitian algebra, and we have a family of elements indexed by the set I and an element B in A, and we have an identity which can be called an infinite distributivity law. The proof of this identity is straightforward from the condition on the implication operator. So let's pick an element. Let's see in A be an element, and then we have the following. Okay, so this establishes the condition on the identity that I stated above. So let me mark this identity like this. Okay, so it is not complicated to show that if A is a lattice with arbitrary supremums, then A is in fact a complete Heyting algebra with implication operator given by the following formula. So A is a complete lattice, or even a lattice with all supremums, complete. So okay, so A can be regarded as a category, and therefore we can try to endow it with gross-induced topology. And there is an actual way to do it with any Heyting algebra, or in fact, I think this will work for any lattice with arbitrary supremums. So the category. So this topology is reminiscent of the open cover topology on a topological space, and for a good reason, because the very basic example of complete Heyting algebra is just an algebra or a lattice of all open subsets on a topological space. So this basis of topology in this case corresponds just to the open cover topology on category of all open subsets of a topological space. Note that AI less or equal to C is guarded here as a unique morphism AI to C. the condition star or infinite distributivity law is in fact just the stability axiom for K. So what is a sieve in this topology? Well, a sieve is just an ideal in this category, and since it is a lattice, it has a particularly nice description. Such that A less or equal than B in S implies that A is an S. In topology J given by K, a sieve is covering if the union of S is equal to C. So this topology is called subtopology on A, and it corresponds to the open cover topology on a topological space. Okay, so now let's return back to our topic of studying exponentials in categories of sheaves and consider the case of complete Heyting algebra. Let A be a complete Heyting algebra. F and G are sheaves on A. If A is an element of A large, then we can define an ideal generated by this element, which is basically a maximal sieve on the element A. So A itself can be endowed in the structure of complete Heyting algebra. And in particular has subtopology. Moreover, if F and J are restricted to FA and GA on this category, then the exponent is a sheaf on A whose elements are natural transformations of the following form. So exponent exponential g to the power of f is a sheaf on A with elements being natural transformations of the form since home BA has only two options in complete Heyting algebra. Such tau is just a collection of functions tau b from fb to fa, sorry, from fb to gb, unique for each b less or equal than a, and natural in b. In other words, gf of a is just a home between the following restricted sheaves. So this formula is in agreement with the formula for topological spaces where we have for two sheaves g to the power of f of u is the same as natural transformation of sheaves restricted to open subset u. Okay, so let me give another example. Let tau curly be a topological site. So an open cover topology or topology of open surjections. Then any x in topological spaces, not necessarily inside of T curly, represents a sheaf on T curly consisting of continuous functions. Okay, so in the case when X is locally compact, and Y is just the topological space, the mapping space Y to the power of X could be endowed with compact open topology. In this topology, we have a map of the following form, and it usually is an isomorphism well, this is an isomorphism precisely when X would be covered by elements of T. Okay. So let me finish my short talk with a small discussion of Yoneda lemma in category of sheaves. Okay, so first assume that J is a subcanonical, meaning that any representable pre-sheaf is in fact a sheaf. So assume that is a subcanonical topology on C. Then we have a factorization. However, so this is the unit embedding, this is the embedding of sheaves into pre-sheaves, and this is the factorization which comes from the fact that the topology is subcanonical. Okay. However, if J is not subcanonical, we still can consider canonical functor AY from C to sheaves on C. And for any sheaf, the unit lemma, so let F be a sheaf. The unit lemma implies the following isomorphism. And jointness from the theorem on sheafification gives us the following isomorphism. So and since any pre-sheaf is a collimate of representables, thus any sheaf regarded as a pre-sheaf can be represented as a collimate. Thus any sheaf regarded as a pre-sheaf I of f can be represented in the following form. Thus, since A as a left adjoint preserves collimets, we have the following formula for any sheaf. So A preserves collimets, thus we have the formula of this sort. F is isomorphic to AI of F because AI is isomorphic to ID on sheaves. This is in turn is isomorphic to collimate of ICK. This is in turn is isomorphic to collimate of AYCK. This in turn implies the following important observation, that AYC generates the category CJ, sheaves on CJ. And by that I mean that we understand that for any two parallel systems Fj from A to B, F is equal to J if and only if Ft is equal to Jt for any T from AYC to A. Okay, so basically that was it. That's it with regard to what I wanted to talk about today. Maybe there are some questions, comments. I'm sorry, my talk today was rather short. But we did discuss some elementary properties of the category of sheaves.